My name is Raghu, and today I'm presenting one of my capstone project, which is done under the guidance of Dr. Sujit Shankar Muni, which is social network analysis on sentiment-aware competitive graph diffusion model for negative information control in online social network. So basically, we are trying to identify or analyze the spread of negative information in online social network. So for that, we have proposing this model that is competitive graph diffusion model, which is based on sentiment of a user. So this project is inspired by a reaction diffusion model, which is one of the research paper that we have studied, and we have further tried to extend this approach by integrating sentiment of the competitive graph diffusion model. So we as a user connected to so many people, and if someone spread any kind of negative information, we get infected, and it depends upon me or us who get this information. We can either spread that information or we can consume that information. So, uh, yeah, let's give me one more example to you guys. Me as a user, I'm connected to so many friends, and we are connected to each other by WhatsApp, Facebook, or we can say Insta. If someone sharing any kind of negative content which is inappropriate, and so I get affected, right? So now it's depend upon me, should I share this information further or not? If I'm a trustworthy person, so having a lot of connections, so make me a second to spread this information among all you, and so all get affected, infected. But if I'm not a trustworthy person, if I'm a trustworthy person, I will not do that things. Okay, if I'm not trustworthy person, then I will. There are high chances that I will spread this negative information. So that's the reason I just tried to model this kind of sentiment aware competitive attribution model as to show you guys like how sentiment and the trust of a user play an important role in negative information spread. So further, I will try to show you what are our previous studies and what we are going to do and what our approach is. So these are the table of content, the problem, the previous work, key findings and previous works, limitations of the previous work, our approach, graph diffusion mechanism, integration of sentiment and trust, which is our approach, and incorporating GCN, graph convolution network, to understand the pattern of spread, experimental setup. These are our experiment done by us, and results and observation, comparative insights, conclusion, future works, and references. So let's see what basically negative information. Negative information, we as a user, as said earlier, like we as a users are connected to a lot of information, and if someone try to damage our reputation, so it kind of distress, right? It kind of a reputational damage and public interest, and it's very real. Like if someone tried to blame you or damage your reputation, you get affected, right? You get distress. So these are the kind of negative information. It's like rumor, defamation, hate speech, or misinformation that is spreading all over the social network. So hence controlling this negative information spread is critical for online safety and social stability. So now let's see what is basically a competitive control mechanism for negative information spread. So this was one of the studies that has been done in the research paper, yeah, which we have taken. It is so author model this information spread as infectious disease. The way a disease spread, same way the negative information is spread in online social network. So initially, we as a user are unaware about any kind of information, and we getting informed by others as we are connected with them. Then we get infected. Then we further share the information based on our trust level or our sentiment. So to study this phenomena, author design of gate created this competitive regulatory diffusion model to show you guys like how reactions basically the reaction diffusion model works, or how the negative information spread in a social network. So as I said, we initially unaware, we get informed, and we then further share the information. So reaction diffusion was basically is like we as a users interact with other people and we change state. Like initially we are unaware and we get infected. Diffusion is like how information is spread from one community to other. That is what diffusion is. So the key finding for the previous paper is like they mentioned three important numbers to show to study the effect of negative information. So first is Arnold one that shows how the ability of negative information to make people infected, to make neighbor people infected. And then we have Arnold one and Arnold two that determines whether the type can invade by another dominance. So Arnold one is basically for you can say negative information, and Arnold two is for positive information. And Arnold is basically a mix of Arnold one and Arnold two. If R naught is greater, R naught is more. That means negative information is present in that particular area, the particular region. And if R naught is more, R naught two is more, then we say positive information is there. And if the value of the R naught is less than one, we say there is no information spread. We can say that it's a kind of free equilibrium state. There is no information is there. And if R naught is greater than one, we say that there is information spread. So based on these numbers, the author tried to simulate the information spread. So based on that, they defined four equilibrium state like information free state when there's no information, negative dominant when there's more negative information in the environment, and the third one is like positive dominant, like there's positive information in that particular equilibrium, and coexistence like this is a kind of unstable state. We call it as bistability when both negative and positive information is present in the network. And we call coexistence of that information. So these are some key findings, and they also discuss about biostability, which I said earlier, like it's a kind of unstable state when both positive and negative information are present in a network, and the final outcome is depends upon the initial conditions. Then we have controlling factors, like how author try to control this information spread. So you mentioned one that is positive rate split, like we can inject positive information to suppress the negative information spread. This is one kind of way we can control the spread of negative information. Then we are managing special heterogeneity, like as they mentioned in the paper, like the information will vary from place to place. There might be a chance in like in one place the information spread is faster, and in another place the information spread is not that much faster. So these conditions both are taken into consideration. Then we have using diffusion coefficient as like it's a diffusion parameter. More the diffusion coefficient, the more is the information spread. That is more negative information will spread. If diffusion coefficient is lesser, then there will be a less information spread. So the key insight from the paper is that positive information can be used as a natural counterforce to suppress that harmful diffusion. That is one of the key findings from this previous paper. Now I will show you like what are the limitations of the previous approach. So, limitation of the previous is that they are not doing any kind of real-time data validation. They are just theoretical simulation. Then we're talking about no. And second point is that there is no graph-based modeling. As we know, like in today's real time, this kind of first data is modeled using graph. So they are not using any kind of graph-based modeling, and we are now approaching this kind of approach that is graph-based modeling, which we are trying to I will explain you further. And there's a limited scalability that is they model this entire reactive model using PD, that is partial differential equation, like how information vary with time, spread respect with vary with time and space. And there's no AI integration. They're not using any kind of existing technologies or the latest technologies like NLP, learning based trust or sentiment model. So this is our approach, which I said, sentiment and trust graphical model. So we are considering each user as a node, and based on the interaction between with other users, like whether we are commenting someone, whether we are following someone, or we are messaging someone. So we are forming an edge, or we are forming an connection with other user. So how basically this model works, like if I am a user, I am connecting to two or three people as to other users. So based on the sentiment of the neighbors and their trust, I can find like whether I get infected with positive information or negative information. If the probability of positive information is more with my neighboring nodes, and the probability of negative information is less, in that case I will get affected with positive information. of negative information, then I get infected with negative information. So these are the three parameters that I have assigned. That is node, sentiment, and trust score. So how basically a graph diffusion model works? So each user might be in three, four states. That is susceptible, that is not yet exposed to any kind of information, that is negative. The users get infected by negative information. The second one is the user get infected with positive information. Then R, that is no longer spreading, they just recovered from that infection. So here you see a small representation as shown as a graph. So in between that negative and the positive node, there is some suspected node which are not yet exposed to any kind of information. If you see the red and green, what I say is the in between gray nodes, the first gray node is connected to a red node and green node. If the probability of a red node, that is of negative information, is more, means their trust and their sentiment is more. Not trust might be lower, but if sentiment is more, then I get infected with negative information. As you see in the next diagram, like I will get infected because probability of negative information is more, and this will further diffusing within the network. Now, to control this, we are trying to inject, the positive information, which is the blue node you see in the above diagram. We are injecting positive information to control this effect. This is how basically a graph diffusion model works in a simpler term. So as I mentioned in the slide, like how it works, a susceptible node become infected based on its neighbor states and trust weights. Sentiment affect direction of spread, trust affect negative influence, and over time diffusion evolves as node changes states. So this is basically with iteration, this everything will change. So this is our integration of sentiment trust. So initially what we are doing is we have a user as a node. We are trying to extract the sentiment, which is basically the comments or messages they do on social networks. So we are calculating the sentiments too. We are calculating the trust score of the user based on degree and page rank, and then we are doing state analyzation. Like we are assigning a random state to just starting our iteration. So we are initializing with each user node with sentiments, where basically a particular state, that is the negative, effective, positive, effective, suspected, or recovered. Then we are calculating the influence of the neighbor nodes, like trust into sentiment into, that is positive spread rate or a negative spread rate. So based on this calculation, we can determine that the other person is affected by positive information or a negative information. So then we are simulating the output like diffusion trajectories and network snapshots and which I will discuss you further. So this is our combined influences which we are calculating from the user, our neighbor user. Now we see integration of sentiment trace. So these are the formulas that we use for calculating the influence on the neighbor. So the first mathematical picture you see, this one is used for calculating the sentiment, the influence of the neighbor, single user. And this is a combined neighbor influence, and this was a combined negative influence of the neighbor. So this is how our a single node looks like. So each user is associated with these messages or comments which they have done in the social network, either commenting on messages. So for that we are calculating their sentiment and trust, as I mentioned. So this was the experiment we have done. So this, which is a synthetic data set which we have taken. We have taken 50 nodes randomly, and we have taken beta positive is 0.3 and beta negative is 0.4 and gamma 0 to 0.2, which is recovery rate. So here in this picture in the experiment, we have shown you like how information is spreading. So initially we are having five green nodes, which is the positive nodes and the three negative nodes. So we are actually showing like how negative information was spreading in the thanks and three. You see like negative nodes are more. Then we see some nodes are getting recovered, getting changed to blue. They also get recovered. Some more get recovered, some more get recovered. And you see the graph. Initially, the negative information spread increased rapidly, but it will stabilize after some time. positive information, and you see nodes get infected and recovered to last stage, and you say suspected nodes are more initially, but it will get reduced to as the time increases. This was another setup where five nodes are taken as most negative and six nodes are taken as positive. So this was done on real-time Facebook comments. Each user is associated with three comments or messages. We have calculated their sentiment and trust. And based on that, we have done this experiment like how information is spreading across time steps. This is your trust score distribution. And what I got to know from this trust score distribution is like negative information is usually spread in lower trust regions. And you see 0.3 to 0.4, they're having a maximum height in this, like maximum number of users in this area. That means negative information is spread mostly, low trust region. That is what the insight we're getting from it. And you see the complex division over time, negative and positive information increases at the initial stage and will get stabilized after some time. This is the kind of analysis we have done. Now, so we have seen this pattern, like how information is spreading over time. Now, the thing is, can we make neural network learn this pattern to predict like how will be the information spread in the coming future or in the coming time stream? So this is what we have done in GCN, it is a graph convolution neural network. So we try to make our neural network learn this pattern and predict future spread pattern and future spread. So this was the architecture which we have done to make our neural network learn. So our architecture consists of GCN layer that will try to learn the spatial pattern, the distribution of the nodes, and we have used GRO as a second layer that is try to understand the, you can say, you know you can say how that spread is evolving over time. So these are the two layers to effectively learn that pattern, predict like what will be the spread after some time. So we have done this experiment. Then this is the experiment setup which we have done. So I'm trying to make neural network learn this pattern. That is the first law representing which I have feed it to the model to learn this pattern. And these are the second law represent these are prediction done by neural network, that is they are trying to learn this pattern. Then it should see uh, this was the true final state which represents the actual spread at time step 35, and this was the prediction done by this neural network, which is very similar to actual. Like so, from this we can see like neural network learning this pattern, and it has achieved accuracy of 79% on a held of nodes. So we can say the model effectively predict diffusion outcome based on the initial conditions, and we say high trust nodes act as a key influential shaping the financial sentiment balance, and it demonstrated graph neural network can predict and generalize social contagion. Contagion is the inclusion spread dynamic better than Google-based model. So instead of just theoretical analysis, we have done this experiment and it's demonstrate like how can the information spread over time, how can this spread. So these are the experiments which we have done. So comparative insight is that so between the reaction diffusion model, which is a previous paper, and our approach, that is graph diffusion. So in previous paper, they have tried to model the information spread as PD, which I have mentioned that how information is spread with respect to space and time. So and here we are coming with discrete graph this approach where the vectors are beta rate, which is as I said, the positive rate of spread, and diffusion parameter. And here we are coming up with sentiment interest, which we assign to each user. And then we have data, which is a theoretical one, and it is a real plus synthetic, which we have done. Learning here, nothing here, but we are doing a learning here is GNN based representation learning. Then we have conceptual control in practical use. Here we have this scalable network analysis. So I said that is section diffusion model is more often conceptual theoretical, but we are doing a scalable network analysis. So the conclusion is the Java proposed model, that is sentiment assessment model, learn the patterns like how information is spread over time and show that emotional tone and use incredibly jointly counts how information spread. So the basic conclusion is trust boosts influence and sentiment shapes by direction. High trust notes that faster state positive diffusion. Negative content spread in low trust region, as I mentioned, as I show you from the trust trust graph. And evolve GCL learn and predict diffusion pattern accurately, and both trust and sentiments are key for realistic modeling. So these are the conclusions. So future work is like right now we have done on static data points. The model future we can make it more dynamic on the real time data set to see the real places like how information is spreading over internet and incorporate dynamic sentiment updates. As I say, the sentiments are static, so it might change with time. So it should be timelistic. So we can use this model for misinformation detection and trust-based prevention. So these are some of the references. These are the comments on the messages that we've taken as a data points from Kaggle, and this was our previous paper. So yeah, that's all about this caption project, which is done by me, Aman Sharma, and my colleagues Sharon George Chako, Mohammed Anshif, under the guidance of Dr. Siju Shankar Mane, Digital University, Kerala. I hope you understand what I'm trying to convey. Thank you. If you have any suggestion, please do comment.